Good morning, everyone. Well, I guess we're getting a little bit of rain. It rains and then it stops, and maybe that's not torrential, but hopefully that's keeping the level of pollen down for those of you that have some issues with that. I think I still do, but I try to do the power of thought just to say, okay, it's just the sniffles and I'll be fine. Um, what we're going to do today will just basically be an extension of the last two sections. That is, we talked about the Taylor polynomials, and that was an interesting construction where we generated these polynomials that could be substituted for the actual function. And then we were able to understand basically an upper bound on the error involved in making that substitution. So that was a really groundbreaking idea. And what we saw is that utilizing polynomials can make computations easier. And then, of course, we look at the fact that the polynomials form the basic groundwork for approximating transcendental functions, or any kind of function for that matter, as long as we can generate a Taylor polynomial. What we want to do today is to actually exploit the geometric series and utilize concepts about power series with the sum of the geometric series, using maybe some partial fraction decomposition, and then using the fact that we can integrate and differentiate a power series within the interval of convergence. And we also know that the radius of convergence is the same as the original series. So we're like, boy, that's a gift. And still, we have to check the endpoints. The endpoints aren't something that we're going to get for free, but it may be useful to us to include an endpoint in the interval of convergence, and that's another thing that can be helpful with computations. So what we want to do, like I said before, is to now look at the geometric series in context with general constructions of power series and see where that is going to get us. And what we're going to find is that once we do these types of constructions, they're going to be exactly the same as basically constructing a Taylor series, just like we did the Taylor polynomial. What we're going to find is that a convergent power series is its Taylor series. So if we actually create a power series via different means, we're still doing the same thing as if we had computed the Taylor coefficients. So that is a remarkable, remarkable fact of modern real analysis that, again, we, excuse me, we get all these gifts, they just drop out of the sky, and we're thinking, this makes our lives so much easier. Excuse me. But the main thing we have to realize is that as we work with these particular objects, we have to respect the convergence that we learn from the real series and then respect the new ideas from the power series. So let me go ahead and share my screen. Now, what I want to do in this particular case, let me get this lined up. I tell you, every time I move something around, I have to remember that my document cam doesn't have a brain. Well, it has a brain, but not the best one. So there we have it. I love my IPEVO document camera, but sometimes I wish it could share my brain. So what we're going to look at is 9.9, and we'll say operations with power series. Now, sometimes I'm going to be lazy and I'm just going to write P period S period for power series, so we don't have to write that all the time, but you'll know what I mean. So let's just go ahead and look at two power series. That is, say that we have a function represented by the following power series, and this is in the generic form. This is written up very nicely in your book. And of course, you would find this in any calculus textbook. And say we have another function that is written in terms of a power series. So with different coefficients, obviously, just kind of like we were doing with sequences before. So what we're going to do again is we're going to look at ways of combining these, and then we want to fix, so some constant k, real constant, and then some natural number n also fixed. So what we're going to do here is for each of these, we can assume that there's an interval of convergence. Okay, so the assumption is that we think, okay, if we work on convergent power series, we will always have to consider the fact that they each have a domain, so to speak. Like in pre-calculus and college algebra, you know, if you added two functions, you had to consider the intersection of their domains. Now we're thinking of a function as being represented by its power series that has an interval of convergence. So we're going to think of the interval of convergence. I mean, I guess we learned everything we needed to learn in college algebra, add some trig to that, and we're fine to do calculus. So the interval of convergence will basically be identified with the domain of the function that it represents. Okay, so now we're heading back to college algebra and thinking about what we did with functions. Well, the first one would be a composition type result. For instance, would it be convenient to replace x with a constant times x? Maybe what we're going to find is that when we work on this particular problem, maybe instead of x, we need 2x, or maybe 1/2 x. So of course, that would just be substituting. So this is a composition, so to speak. So very simple. So now, of course, if you looked at this, you could just use your laws of exponents if you wanted. So this is a very basic operation, saves us some time. So we'd have k to the n, x to the n. And we've already seen that at work when we work with our power series. We use the laws of exponents all the time, and that's a natural thing. The next thing would be maybe we need to replace x with x squared. Maybe that would be a more convenient power series for us. So we'll say f(x) raised to some natural number. So again, this is a composition. So we have n equals 0. We'll have a sub n. And now we'll just replace x with x sub n. And now, of course, when we use the laws of exponents, we just multiply the powers. So we get a sub n, x to the n times n, like that. So this is not something you don't already know. I mean, I'm not, you know, like, oh wow, this is earth shattering. You already know this. We've actually been doing this, but it's actually comforting to write these things down, to know that what we've been doing is actually justified. And then, of course, you're thinking, we eventually will probably try to multiply power series like polynomials and maybe divide them. We'll talk about that in the next section. But for now, we're just going to be contented with the fact that we can add and subtract them. So this will be the third operation. So again, if we treat the infinite series, the power series, in the finite case, we can always treat them like polynomials and start the multiplication or division process to generate enough terms of the series. Because when you think about it, all we really need is enough to get a decent estimation of the function. That's the key. So when we do this, we're just thinking of adding the two series. So we can just combine the nth terms, so to speak. We have the a sub n plus or minus b sub n, x to the n. And then, of course, in this case, this may require that we check the interval of convergence. That is that if we've changed it any bit, or we have to maybe diminish it. You know, you think about adding two functions, you certainly can't substitute a particular value of X, it's not in the domain of both functions. That's why we always think about intersections. So nothing that we have done before will be something that will get thrown out. We'll just keep it. We'll keep it in our bag of tricks, so to speak. Now, I want to mention the geometric series. We have a notation that we've used pretty much throughout, but now we want to modify it. So before we could sum it. That is A divided by 1 minus R. And here was one of the notations that we used. That is, we could say n equals 1 to infinity, A R to the n minus 1. That was a notation I often used. And then, of course, when we work with power series, lots of times we want to start at 0. And again, don't worry about re-indexing. Maybe if you start at 0, and change things around, you're just adding 0 and you're thinking, why am I doing that? Well, sometimes notationally it looks better, but we just have to be careful that whatever we do when we're adding series like we're doing here, that we have the same powers. You can't add x squared and x cubed. Okay, so if we have to readjust powers in the power series so that we've got like terms, then we will have to do that. Otherwise, we're stuck with leaving them separated. So for instance, if we looked here and made a notation, that is, we replace n with n plus 1. Sometimes I'll just do a little arrow, n becomes n plus 1, instead of saying replace. This is a common notation that I use. And if you do that, for instance, if n becomes n plus 1, then we're going to have to start the index at 0 because we've added 1 to what we have here, and we want it to be equal. So in increasing n by 1, we must start at the initial index of 0. And then, of course, if n becomes n plus 1, the 1 and the minus 1 absorb, and we get this. And this is an alternative way of writing the geometric series. So now, one of the forms that we enjoy a lot in working with power series is we set A equal to 1. And I could say n or R becomes X. I'll just write this out because this is a different variable. Replace R with X. Because notice we use X's here. And so we just want to make it a little bit more user-friendly. So we could say 1 over 1 minus X equals the series n equals 0 to infinity of x to the n. And then, of course, if we wanted to write out several terms, this is our friend. And of course, if we did the Taylor polynomial, it would look the same. And of course, this would be the Maclaurin because c would be equal to 0. So this series is our friend. We depend on this series. And now today you're going to think, I'm so glad we know the geometric series. So that's what usually happens in a calculus text, ladies and gentlemen. There's the author or the math professor will devote a lecture to manipulating the geometric series. So let's go ahead and do that. So again, this will be kind of our tool. Now just remember, just from the theory that we developed here, we know we have convergence for absolute value of x less than 1, or sometimes we want to make it maybe a little more user-friendly, and we'll say x in the symmetric interval. So just like we have to solve the conjunctions via the ratio test, we'll be doing the same thing here. We may have to focus in on what's the new R, so to speak. Notice now we may manipulate things, and whatever ends up here becomes the new R, and then we have to actually analyze this particular inequality to maybe get a different interval of convergence. So what's nice about the geometric series is that we already have a lot of the difficult part that is available to us. We don't have to use the ratio test and figure out the interval of convergence. If we start with this, we already know what it is. And then, of course, if we apply differentiation or integration, we're pretty much going to have to check endpoints. But if we don't do either of those, then we're pretty much stuck with the case that we won't get the endpoints. You can always check them. And I tell students, I said, I don't want you to think that I'm being negligent in this case. But in the situations where we're not doing integration or differentiation, I'll just say, well, there's no need to worry about the endpoints. So let's look at some examples. Again, I think this is one of the most satisfying sections of the chapter here. So let's do this. Let's write the function as a power series. And so in this case, I'm going to say as a, and I'll do P period S period power series. And in this case, what we'll do is we'll take C equal to 0. So what we're thinking of in this case is that if we're going to use the power series and we're going to think about how we actually do this construction, then we will exploit what I just wrote about the geometric series. So here's an example. G of x equals 4x divided by x squared plus 2x minus 3. Say we're given a function like this and we're thinking, okay, well, maybe we could rig this with the geometric series, but first we're going to have to break it down. So we're thinking what we're going to do is partial fraction decomposition to give us two functions that we can adjust to the geometric sum and then work backwards to write the power series. So here, this is where we start. So we're going to say g of x equals 4x, and then we can easily factor this. Don't we wish all factoring were this simple? So we'd say x, in this case, plus 3 and x minus 1. Again, this will give us the negative 3, and the negative x and the 3x will give us the 2x. Now, of course, we're back to integration problems where we need a partial fraction decomposition. So we've got two distinct linear factors, and that's the easiest possible case. Here, let me take the brightness down just a little bit. I don't want it to look like can't see. There we go. That looks a little better. So we're going to have a divided by x plus 3 plus b divided by x minus 1. So the idea here in this particular problem is to look at this just like an integration problem. And now when we look at these, we're thinking, well, we can rig these to be sums of geometric series. So first, let's go ahead and clear the denominators. So equivalently, again, we don't have to take derivatives here. They're not nearly as long-winded as some of the other problems. So again, this will give us a times what? X minus 1 plus b times x plus 3. So upon clearing the denominators, this will give us 4x equals a times x minus 1 plus b times x plus 3. And then, of course, we can use some convenient values. First, we'll use x equals 1. So when x is equal to 1, we get 4 equals what? 0 plus b times 4. So clearly b equals 1. And then what we can do is we can get rid of the fraction here by choosing x equal to negative 3. Kind of reminds us of the telescoping procedures. So of course, negative 3, this will give us a negative 12. And of course, here, negative 3, this will be a times a negative 4 plus a 0. And now if we divide negative 12 by negative 4, a equals 3. So when you look at both of these computations here, we now can rewrite G as a sum of two rational expressions that can be rigged to be geometric. So now equivalently, G of X equals 3 divided by X plus 3 plus, now we have 1 divided by X minus 1. Now these aren't quite the form of the geometric sum, so we're going to manipulate them to make it that way. So first, what we're going to do, and I normally do it this way, ladies and gentlemen, to get rid of the riffraff. If we got riffraff upstairs, I just move it out of the way, and I'll just do the 1 over the 1 minus X, and then multiply back through as we need, just to make the formula a little bit more simple. And so we have a 1, and then of course we have the 3 here, but we need a minus X, so we're going to do minus a negative X. I mean, that's cheap, but it works. So the key here, at least at this point, is to say we need in this particular case a minus R, so to speak. So we've got this, and then of course that's going to need to be a 1. So we'll do that. So again, remember, this is the goal right here, 1 divided by 1 minus X. And then we may have multiplying coefficients, and of course the X may look a whole lot different, but that's the goal right there. Now, when we look at this one doesn't look half bad. We can just go ahead and factor, of course, a negative 1. So we'll do minus 1 minus X. So if you factor the negative here, that'll give you a 1 minus X, and just pull it out to the left. And so that one's good to go. That's already the geometric sum. So that was a freebie. So now we need to factor the 3 downstairs. So this will be 3 over 3. Now, the order I'm doing this is not unique. I mean, I'm just doing it in a way that seems simple. So of course we factor the 3 here and the 3 here. So this will be a 1 minus negative X divided by 3. So again, when you multiply by the 3, you retain the 3 here, and of course the 3's absorb, and you have exactly that. So now we have the 1 divided by 1 minus the new X, so to speak. Okay, so this has the right form, and this of course has the right form. So we say minus 1 minus X. So now when we look at these, we're like, wow, that wasn't so bad. This has the correct form. This has the correct form. So we'll just say geometric sum. So this is the song and dance that we do. This one was just super simple, geometric sum. All we did was factor a negative 1, and we get the formula for free. So now we can work backwards to the power series. So there's the new X, the 3 over 3 is just 1. So we get series n equals 0. And now the new R is what? We've got what? Negative X over 3 to the n. Okay, so that's the geometric power series right there. And then of course that's just the X to the n. So we have minus n equals 0 to infinity X to the n. I guess we wish all of them were that simple, but usually what's going to happen is that we've got to do more work like we do here. And then sometimes we may have to shift because maybe we're not working with a C equal to 0, and then shift it and then adjust it to make it look like the 1 over 1 minus X. So now when we look at this, let's go ahead and use some of the properties of the power series that I mentioned at the very beginning of the lecture, just to make it look a little easier. So now, of course, notice we have a negative 1 here, which will give us alternating. So you can go ahead and pull that out, negative 1 to the n. And then, of course, we have X to the n. And if you like, you can just put 3 to the n downstairs using the laws of exponents. So now you're thinking, wow, look at this. This is all good to go, because now if we subtract the other, we can use the last property. Notice now we have the same power of x, so we can add them, in this case, subtract. We have the same power of x, so this is just like the last property. So we can merge these. So now we have n equals 0. It's amazing how we have all of this ability to make power series using a construction from pre-calculus. That's amazing. So now we have what? -1 to the n, 3 over n. Of course, and it doesn't really matter if you don't make it look like this. As long as it's equivalent, it's fine. It doesn't matter. You can just have -1/3 raised to the n power. I just break it up because it reminds me of our ratio test, but it's your choice. -1 x to the n. So when you look at this, this is a power series for this function. Now we need to go back to what we had up here and check out the new x's. So for the first power series, we have the absolute value of -x/3 must be less than 1. And then of course for this one, we just look at the x and absolute value of x must be less than 1. Okay, well, that one we know about, but here this just means multiply by 3. So equivalently, we have the absolute value of x less than 3. Don't we wish all our problems were this easy? And so, of course, x will just live between -3 and 3. And here, x lives between -1 and 1. Okay, we need both of these to be true. So we certainly couldn't use this. We have to take the intersection. So this would mean here that x would have to live between -1 and 1. Clearly, we have a larger interval of convergence here, but it's certainly not seen here. So this would be the final construction. So again, just like you do in college algebra, but maybe on a higher level, right? So when we think about the geometric construction, we're seeing basically that we look for functions that have that geometric sum look, that rational function look, 1 over 1 minus x. But we may have to work harder to get it into that form. So what it basically means is that the goal, and you can see how I've done this, we want a 1 divided by 1 minus the new x. And that will be the geometric sum. And then whatever riffraff you have, you can multiply in. We can always multiply a power series by x or a power of x. That's so simple. I mean, it's a very interesting finite power series, right? And so we can use basic algebra to make new power series without having to start from scratch. Now, of course, here we may find this to be useful in a computation in a engineering problem, mathematics problem, physics problem. So again, the beauty here is that since we already have a good understanding of this, this may not be as monumental as maybe a power series for sine x or something of that nature, or e to the x, right? We already know what they look like, the Maclaurin forms from the Taylor polynomials. Now what I want to do is just jazz this up a little bit, and then we're going to talk about two interesting examples having to do with integrating and differentiating power series. We already know how to do that, but we're going to actually practice it based upon the geometric technique. And these are standard examples that you always cover if you've taken calculus. I mean, you have to see these. So the next one is just another example of the power series method. And I want to discuss this just to give you a little extra practice. So we want to write a power series and interval of convergence for the function. So in this case, we jazz it up a little bit. That is the function. We're not going to have to do a decomposition on this. We're just going to have to do some additional algebra. So we're going to have the function 4 divided by 3x plus 2. And we want the center in this case to be 3. Okay, so this is just going to be a little extra work. but we don't have the partial fraction decomposition in this case. Now, when you think about this, again, the goal is 1 divided by 1 minus x. And how you get to that, again, is algebra. So your methods, as long as they're legal, will be more than sufficient. So first, when you think about this, you're thinking, okay, we're going to use the geometric strategy. And when I say geometric strategy, the geometric series. So now we have f of x equals 4. Now, the first thing we want to do, and this is usually like doing your transformations in college algebra, is go ahead and input the new center. That is, subtract 3 and add 3 relative to the x. That way you get the new center, and then you can do the algebra to clean it up, and then move to the 1 divided by 1 minus x. So we'll have 2 plus, so we have 3 in this case, x minus 3 plus 3. So this is going to introduce the new center here of 3 by the term x minus 3. But of course, we have to pay for it. So these two expressions are equivalent. So now let's just do basic algebra. So for the type of problem here, the first thing you need to do is introduce the new center. Always do that first. That's kind of like what you did in college algebra when you were shifting things around. So now what does this give us? This gives us a 2 plus, so now we've got the 3 times the x minus 3. And then, of course, we have a 3 times a 3, so that's plus a 9. So it's starting to look better already. So now we get 4, very simple. 9 plus 2 is 11. And we have 3 x minus 3 here. Now, at this point, what we're interested in is making sure we have a 1 here, and then we can dress it up. We get the 1 minus x. So let's go ahead and extract all of the riffraff that's in the way. First, like I said before, the 4 we could leave upstairs, but go ahead and pull it out. Just bring the 4 out. So let me write it this way. Let me not put the fraction bar all the way. I'm going to use a bracket. So use a bracket here. So we have the 1. Leave plenty of space so your work's not crowded. And then, of course, the 11 we need to extract because we need a 1 there. So this will be a 1 plus, we've got 3 over 11, x minus 3. So when you look at this and you think about what we have here, we're almost home free. We've got pretty much everything that we need. Now, just to make this look a little bit more user-friendly, we need the minus minus because we need the 1 divided by 1 minus x. So let's put in 2 negatives. Again, same old song and dance like we did on the last problem. So we do minus, and then another negative. So we'll have negative 3 over 11 x minus 3. So now what we can see in this particular case is that we have a new x. It is very complicated. Notice we put the 2 minuses to mimic the plus. So we have 1 divided by 1 minus x. That's the new x here. So now this is geometric sum. So again, just to make everything clear, pull everything out, achieve the 1 divided by 1 minus x, and then you're good to go. Now you can write what's in the brackets as a geometric power series. So this will give us, now we go back to the crutch that we have, 4 over 11 infinite series n equals 0 to infinity. So now let's throw all that in. So we have negative 3 over 11 x minus 3 raised to the nth power. Now, like we did before, and this is your choice, we can go ahead and dress this up a little bit. There's nothing wrong with this, that this works, but if you like, we can just kind of bring the 4 over 11 inside and use the laws of exponents here just to clean it up. No big deal, but we're used to seeing this when we do our power series problem. So let's clean this up a little bit. So this gives us 4 over 11. So we have n equals 0 to infinity. And now, if you will, we got the -1 here. So we have a -1 to the n. We have a 3 to the n. And then, of course, we have an 11 to the n. And then the x minus 3 to the n. So we just have a bunch of n's running around. And now, if you like, you can bring the 4 over 11 inside. I guess you could leave it outside. It doesn't really matter. But if you want to bring everything internal using basically properties of sums, we'll have -1 to the n times a 4 times 3 to the n. And then, of course, downstairs, we're going to have one more copy of the 11. So we have 11 to the n plus 1 x minus 3 to the n. So when you look at this and you think about what we've done in this particular case, you're thinking, okay, now we have a setup that expresses this function as a power series. Maybe the problem that we're working on requires that we have this expression. Now, again, when we look at this, we think, okay, where would this be valid? So what we can do is basically go to the R, or the new X, so to speak. It's right there, it's right there. So let's analyze it. So for the convergence, we have -3 over 11, x minus 3 in absolute value, less than 1. So we get that for free from the geometric theory. So now, if you will, we've just got 3, apply the absolute value, 3 over 11, x minus 3 in absolute value, less than 1. And of course, now just multiply by the reciprocal. So we have x minus 3 in absolute value is less than 11 over 3. So at this point, if you think about this, we just want to add 3 to both sides. So equivalently, before we do that, we'll have a -11 over 3 less than x minus 3 less than 11 over 3, just the conjunction theorem. Now add what? 9 over 3 if you want to get a common denominator. So a -11 over 3 plus 9 over 3 is less than x less than 11 over 3 plus 9 over 3. So now, of course, when we do the arithmetic here, we get a -2/3 less than x less than 20 over 3. So this gives us the new interval of convergence. So now we can just go up here and say x element -2/3 20 over 3. So for instance, you can check this. I like to always do little calculations on the side. 0 is in the interval of convergence. So of course, f of 0 is 4 over 2, which is 2. But if you were to substitute 2 in here, excuse me, 0 in here for x, you would get 2. Let me just show you that. I thought this was interesting. So let me just do a little observe here. Observe. Because of course, if this is true, then this will mimic this as long as we live here, okay? This is identical to this as long as x lives in here. That's what we have to know, especially since the interval of convergence is not all real numbers. Okay, so if we observe that f of 0, in this case, is just 4 over 2, which is 2. So then we should be able to verify this. So let's just see. So now from the series, we get n equals 0 to infinity. I mean, you know, there's no reason to be afraid of the series. It's just an object that does the same thing, but maybe in a more convenient way, depending on the problem you're doing, times a 4 times 3 to the n. And then, of course, now we have 0 minus 3. So this is just negative 3 to the n. And we have 11 n plus 1. So we have the series n equals 0 to infinity. Just a little sidebar here. So now notice we've got an extra copy of negative 1. So we have negative 1 to the n, negative 1 to the n times a 4 times, and now of course we have a 3 to the n and another copy of 3 to the n. So that's going to be 3 to the 2n. So let's just see what we have, or we can just do 3 squared, which is 9, divided by, and I'll write this since we're going to have a power here of n times an 11. So we have n equals 0 to infinity. Of course, now this is going to be negative 1 raised to the 2n power. So negative 1, n plus n is 2n. That's just going to be 1, okay? And then we have times the 4. And this is just going to be 3. This is just going to be 3 to the 2n, which is 9 to the n, just using the laws of exponents. So we have 9 to the n. And then I'm going to write this first, the 11, and then the 11 to the n. So that's going to be the geometric part right there. We expect this to be geometric. And so now this gives us, so the 4 over 11 is just going to be factored. Well, obviously I'm just working backwards. That's probably not a surprise to you. And that's just a 1. So we get 4 over 11, n equals 0 to infinity. Again, we've got the 1 here, and then we get the geometric part. So this is 9 over 11. I mean, this would have to converge because this is in the interval of convergence. If this were too big, then our theory would be wrong. And so now this gives us what? 4 over 11 times 1 minus 9 over 11. But this is 4 over 11. So this is 1. Of course, that'll be 11 minus 9. So that's 2 over 11. So this gives us 4 over 11 times 11 over 2. The 11's absorbed, and 4 over 2 is 2, as should be the case. So I don't want you to be afraid of the power series. And it's weird, you know, as I sit here and think about things and as I write notes, I mean, I do research every day of my life in mathematics, as I also do in music, because it's just how I think. And when I write down mathematics, I think of different ways to explain something and come up with something. It's like, well, I don't want the student to be afraid of this power series. As long as we're in the interval of the convergence, then we get the correspondence between the actual function we're representing and the power series. We would have to. So again, you don't want to do this every time. You're going to do your calculations and be assured that this represents this function on this particular interval. So there is nothing abstract about a power series. If you just think of the fact that this is just the fancy arithmetic we've been doing from day one, and I think that's what you have to start looking at calculus differently. You can't think of it as, oh, this is tedious, I've got to use my computer algebra systems. No, that's going to make you less smart. That's going to put you in the wrong setup. You have to work the mathematics just like you're in a college algebra class or an algebra 1 class where you're working with the numbers and working with the arithmetic. That's what gives you what you need. Now, what I've labeled here next are important examples, and you see these written up in any calculus book, but they're examples you need to see because they're very important. So what I was saying before, we will sometimes adopt this procedure we're doing now because it's easy. And we think, okay, Taylor coefficients aren't that bad, but you got to compute a lot of derivatives. Then you've got to evaluate them. And you're thinking, maybe this procedure is not so bad. So what I'll do here is just an important example involving the arc. Well, I'm going to do the arctangent, but I'm going to start out with the natural log. So this is important example. So these techniques you can use, long after you get out of this class, especially in your physics, engineering, differential equations, PDEs, all of that. So let's look at f of x equal the natural log of x. We know that the natural logarithm function is very useful, but it has its issues. It has its issues. This is only defined for positive real numbers. So what we know, we're going to write down what we know and rig this for geometric. We know, in this particular case, by the definition, that 1 to x of 1, this is why I gave you the indefinite integral notation last class, because I don't like the way the notation is abused in most textbooks because it's not clear. Students always say, well, why don't you make it easier? I said, well, if I make it easier, then the notation is incorrect. I rarely ever lower the level of notation unless it's just convenient and everybody understands it. If you write notation that is ambiguous and you just continue to push it through, you're going to get to a point to where it falls apart. Okay. So if you adopt bad notation, it's going to make you poor at what you do. And so I have no regret in my career in mathematics that I've always adopted a notation that is at least usable and that communicates clearly what we want it to do. I think Einstein said it best. Don't make anything more difficult or easier than it is. Just state it the way it is. And if you do that, then you always have a foundation. Okay, so when you took Calculus 1, you remember seeing this. Now, this, well, if we just wrote it out, this is the natural log of t evaluated from 1 to x, even though we don't need to do this. And of course, this will just be log of x minus log of 1, which is log of x. So we kind of beat it to death when x is what? Positive. That's just basically the definition. Okay, so when we look at this, we're thinking geometric, 1 over t, geometric. All right, so we're going to do the same thing we did before. We're going to integrate term by term, and then boom, we have a power series for free. Okay, so this is a nice technique. So first, we'll say take what we know. This is where we have to start the problem. The natural log of x is now the integral 1 to x. Now 1 over t, of course, we got to rig it, don't we? Have to rig it. So we say t plus 1 minus 1. I mean, that's pretty cheap, but it's going to give us a 1 that we need in the denominator. Not maybe where we actually need it. We're probably going to flip things around. So I'm going to say dt. So now I'm going to rewrite it a little bit. So this 1 here, I'm thinking I can write this as 1, negative 1 minus t. So we'll do 1, 1, and then we'll have plus negative 1 plus a t. So basically here, we take the add 1 to subtract 1, then we rearrange it, move the 1 up front, and then we put the negative 1 with the t, and then we want to factor this so we get the minus. So This is some cheap algebra, but it gets us where we want to go. So now we have 1, and then we have 1 minus the negative of this, which flips it around. Okay? So the same song and dance. That's why I did 2 examples of this before. This is a critical technique, okay? This is like doing integration. If you don't get this, nothing that I'm going to say for the rest of this chapter will make any sense to you, okay? So you need to master this. So just master it, all right? Now, this is geometric right here. We got the 1 divided by 1 minus x. This is geometric. I know you're not in the first grade and I say geometric, but it's important. Okay, so now we can write this as a power series, interchange and integrate term by term. So now we have the integral 1 to x of the power series. Now, what's interesting about this is that we've got the x right there. So we have t. This is so much fun. And let's see here. I've got the -1. Let me just make sure I've got all my numbers the way I want to have them. So let's see, that's going to be a, I'm going to need an extra negative here because notice what I did here. When we add these together, notice here that we have what's left. These absorb, right? And we get the t. But now here, I need an extra negative, as you can see, because when you add all this up, we just get t plus 2. So I need an extra negative. I thought that looked a little weird. So we need the extra negative here. See, I turned it around, but I didn't put in the negative. There we go. I just wrote it in a different order, so I need my negative there. So make that note. Let me write this so you can see it. Just changing the order doesn't change the sign. So there we go. There we go. So now when you look at this, you can see that we actually get the t, and here you can see that we get the 1 minus 1. So these are equivalent. So now the new x is the negative of t minus 1. So we have the negative of t minus 1. So always check your algebra. There's no harm in doing that. Again, if I just write this as t minus 1, I haven't imparted another negative. And so when I put the negative out front, I need to actually place the other negative so that these are equivalent. So that's important. So now we have written this geometric here series. Let me just say this is the geometric sum. Let me write it as sum. The geometric sum now as a power series. So now we put our dt here, and now we can integrate term by term. So this will give us the series n equals 0 to infinity. Now what we want to do is add 1, divide by the new power. So when we look at this, if we add 1, we get n plus 1. So we can go ahead and write this as a negative 1 to the n, t minus 1 to the n plus 1 divided by n plus 1, evaluated from 1 to x. So again, just go ahead and pull off the minus 1 to the n right here, just to write it to the side so it's easier to compute with. And then when we integrate the power function, add 1, divide by the new power. So when we flip, we can integrate term by term, and now the fundamental theorem of calculus. So this will give us, let's apply x, substitute x for t. So we get the series n equals 0. And of course, my choice here of 1 is from the definition, which will zero out the other term. And you don't have a c to worry about, which is what is problematic with most texts. So we get a negative 1 to the n, x minus 1 to the n plus 1 over n plus 1, and then minus the series n equals 0 to infinity negative 1 to the n. Of course, now we have 1 minus 1, so this is 0 to the n plus 1 over n plus 1. But of course, when n is equal to 0, we just get 0 raised to the 1 power. So this is all well defined. We don't have to relax our notation like we've done before. This is just 0. And this is a better way to do it. Actually, it's a correct way to do it. So now you get log x is this series here. And then we'll figure out the radius or the interval of convergence. Again, there are adjustments to these series that help your calculator to function. So here's a power series for the natural log of x. Now, where is it good? Okay, well, let's just check here. We have our new x, so to speak, right here. I mean, when we do this, and once we move to this point, we've got the what in this particular case. And again, when you think about a geometric series and how you've actually generated all of this, you're thinking, okay, well, we've got this x minus 1 that's raised to the power right here. And then we say this in absolute value must be less than 1. So for convergence, we have x minus 1 in absolute value must be less than 1. So equivalently, we have negative 1 less than x minus 1 less than 1, add 1, negative 1 plus 1, 1 plus 1, equivalently 0, x, and a 2. So at least for this theory, we see that x can live between 0 and 2, and this function is represented by this power series. Now we're thinking, okay, well, so what's going to happen at the endpoints? Let's just see if we can add 0 or 2. Maybe we can't. Let's just check. So check x equals 0. These are important, and you can apply these to any type of problem where you integrate term by term. So now we can replace, for instance, x with 0. So this will give us the infinite series n equals 0 to infinity. That's why it's always nice to pull off the negative here. And so we get negative 1, again, 0 minus 1, n plus 1, divided by n plus 1. So we have n equals 0 to infinity. Of course, now this will just give us negative 1 to the n times negative 1 using the laws of exponents. So this gives us 2 copies here. So we have our friend negative 1 to the 2n times the negative 1 divided by n plus 1. Of course, this now, because of the 2, is just 1, and we can factor the negative. So this is the negative of the series n equals 0 to infinity of 1 divided by n plus 1. But we know this clearly diverges. This is a problem from the integral test, easily shown, diverges by integral test. You could do that in your head. So we exclude x equals 0. So at this point, when we get to real series that are straightforward, we don't have to do a complete analysis since it's a problem we've already done before. And so we're like, okay, that's just going to be a natural log of x plus 1. And as x tends to infinity, that becomes infinite. So the improper integral doesn't exist. Therefore, the series doesn't exist. So that's something we can rely upon as something we've already computed, that we don't have to start from scratch. So now, so no good for that. Let's check x equals 2. So let's go back to our series right up here. So we have n equals 0 to infinity, negative 1 to the n. Now, of course, 2 minus 1 is just 1. We love 1 to any power here, as long as it's not indeterminate, we're fine. So that's just a 1. So now we see we get an alternating series. So we get -1 to the n over n plus 1. And of course, now, if we let a sub n equal 1 over n plus 1, we get, again, this approaches 0, and this is non-increasing. We've done this problem many times. So this particular real series converges. So this converges by alternating series test. So this means we include x equals 2. So again, we just have to make sure when we're doing these problems that we actually get the correct x. And of course, if you make manipulations and things, just go back and do a once over. You know, if something doesn't look quite right, just make sure that when you distribute the negatives, you actually get t, because all of these are equivalent. And of course, we can make them not equivalent by leaving out a negative. So always do a double take. So now we have our series here, and then we can go up and say for x living between 0 and 2 included. So that's log x. Log x equals, as long as x lives here. So we can use our calculator for that. Now, the thing that's interesting here is when you think about this particular series, let's just write out a couple of terms. So when x is equal to 0, we just get the 1. So we get what? X minus 1 over 1. So we just get what? X minus 1. When x is equal to 1, we get a -1. So we get what? Minus x minus 1 squared over 2. Very simple. X is equal to 2. Now again, we get the plus. So we have x minus 1 to the third power. Divided by 3, etc. So this particular series is really nice. So lots of times when you have charts of power series, you'll have the general series, and then you'll have a few terms written out for you. Okay, and again, the idea, I've done several calculations here where you try these out, and the beauty is here is that you can do a small calculation here. I'll show you. I computed log of 1.2, and since this is alternating, you can use the error bound with the first neglected term, and so that makes the error analysis easy. And so again, you're thinking with logarithms, you can also use the logarithm identities to manipulate logarithms to make the process of convergence even better. That's also true with the arctangent, which we're going to talk about now. So what I want to impress upon you is that this particular technique relies upon the indefinite integration that I've reminded you of from Calculus 1, and then the ability to integrate term by term, of course, utilizing the construction of the geometric series. So this is a very, very elegant technique. And you can see that we get so much output just by using the geometric series. It's an amazing technique and an amazing fact of real analysis. So the next important example is that of the arctan. So we're going to let f of x equal the inverse tangent. Of course, when you use Google, that always comes out as arctan, which is fine. But now, one thing that we like, the inverse tangent of 0 is 0, okay? So I'm thinking if we write our indefinite integral with the lower limit 0, it's kind of like using the lower limit of 1 for the natural log, which is 0. So that's like, yay, that gives us the constant that we need, and we don't have to abuse the notation and write things that are basically false. The thing that bothers me the most is that inattention to notation means that you're not caring about what you do. There's not a single part of the problem that's unimportant. I'm meticulous about making sure signs are correct and things are done correctly. because our brains work a certain way. We do one task and then we forget something else. So we're always having to go back and check what we do. So we think about how we did the last problem, and that gives us a way to construct the present problem. So what do we know? We know that the inverse tangent of x, just using the very first week of this class, will be the integral of 1 divided by 1 plus t squared. And of course, I'm going to be lazy. I'm going to use 0 to x dt. That's basically the definition via the integral. We define the inverse tangent based upon its the tangent function. But in terms of an integral, boom, there it is. Remembering that the inverse tangent of 0 is 0. So you're thinking, wow, this is easier than the last one. That's geometric. We just put in 2 negatives, we're good to go. The logarithm, again, you've got to add and subtract the 1. Then you've got to negotiate the negatives. And you end up with an alternating series, which is great because then you've got that nice first neglected term error bound theorem, which we love. I mean, let's face it, that's a very, very useful technique that many of you have mastered, I've noticed, and I'm very impressed with that. Now we can say, all right, this is geometric, use the same technique. So this implies inverse tangent of x will now be the integral 0 to x. And so let's do the same song and dance. Don't have to work hard this time. So we have 1 minus negative t squared. Again, the manipulation part is probably the most difficult because it's the strangest thing we're doing. We're fine with integrating, we're fine with substituting, we're fine with absolute value, but this new technique is a little strange. So now this is a geometric sum. Geometric sum. So now we can replace this particular geometric sum with the power series. Didn't have to work hard at all. So we have 0 to x. So now we have the infinite series, n equals 0 to infinity. There's the new x, so to speak, negative t squared to the nth power, dt. And then we interchange the sum and integral to do the what? Term by term integration. Again, operating within the interval of convergence, which we assume is bigger than the empty set or 1 point. So now we have the series n equals 0 to infinity. So now we can look at this and say, okay, just like we did the last problem, we can integrate term by term. Now notice here, when we flipped, I went ahead and added 1 divided by the new power. We can do that again, or you can write the integral again. It's your choice. So now we integrate term by term. So we're going to say negative 1 to the n. Just go ahead and pull off the negative 1 here. And then we're going to have what? 2, or t, we've got to the 2n, add 1. So we have 2n plus 1. So like I just said, if you want to add another step, you can. It's just easy just to go ahead and add and divide by the new power, add 1, divide by the new power. So you can write this in if you want. And so now when we add 1 and divide by the new power, we get 2n plus 1 divided by 2n plus 1. Evaluated between 0 and x. So the key here, and this is what's extremely important when we think about this. Just like we had before, we can do the term by term inside the integral. Add 1, divide by the new power. Now evaluate n equals 0 to infinity. So we have -1, replace t with x to the 2n plus 1 divided by 2n plus 1. And now replace t with 0. So we have n equals 0 to infinity, -1 to the n, 0 to the 2n plus 1. We're not going to have any problem because when n is 0, we just get 0 to the 1. That's defined. And this term from the definite integral or indefinite integration is 0. So what are we left with? I'll just do an if and only if. Inverse tangent of x equals this series right here. So the constant, again, turned out to be 0. And this is just a better way of doing it. Students just start slapping constants around and don't really know what that means. The idea here is that when we interchange, we're just doing a power function. And then when we apply the fundamental theorem of calculus, we get the 0 here that we need via a way that's easy to understand. And now we have a power series that represents inverse tangent. And now we think, okay, well, where are we? Where are we? Okay, we go up here and say, oh, there it is. We've got this x, so to speak. You know, when we do this particular analog here, we're thinking that's the geometric. That's the problem right there. That's the new x, so to speak. So where do we have convergence? So let's just say convergence. And if you want, you can write that as a t, but just go ahead and write it as an x. So we have negative x squared less than 1. That was the new x, even though it's written in terms of t because of the indefinite integral. And that's what we use to write the geometric series. So go ahead and just say you can do negative t squared or negative x squared. Go ahead and write it as x squared if you like. And so the negatives absorb. So this is just going to be the absolute value of x quantity squared less than 1. Apply square root function, increasing function. So equivalently, the absolute value of x is less than 1. But so when we look at this, we just say x lives between -1 and 1. So when we look at this, we think, well, this is like we had with the natural log. What happens at the endpoints? Well, let's check. So we'll check x equals -1. So we get the use of modular arithmetic here. So now we've got this. So we've got the integral, or excuse me, the series n equals 0 to infinity, -1 to the n. So now we've got what? -1 to the 2n. And I'm just going to go ahead and write the -1 here to the 1. Just say 2n plus 1. So -1 to the 2n, and then that. But I don't think that's going to help me. Let me just go ahead and leave it where it is. We'll just do plus a 1. That's fine. No need to do that. And then we have 2n plus 1. Okay, so now let's see what we get. Let's use the laws of exponents. So we have -1. So now we have an n plus a 2n, that's a 3n, plus a 1, divided by 2n plus 1. But of course, parity is built on modulo 2. So we see 3n plus 1 is congruent to n plus 1 mod 2. That is, 3's are just 1's. When you divide 3 by 2, you have a remainder of 1. So this is just equal to, I mean, if you like, n equals 0 to infinity, -1 to the n plus 1 over 2n plus 1. But that's just a nice convergent alternating series. So we could say a sub n, in this case, equals 1 over 2n plus 1, which clearly goes to 0 and is non-increasing. Well, you know, thank goodness for the alternating series. So we'll say converges by alternating series. Alternating series test. So we include -1. Well, let's check 1. At least when we do this, you get to review everything we've done before. We use the integral test a lot, the alternating series test a lot. I mean, we've used the comparison test. I mean, all of it gets used. So now here we go to our series. So we have n equals 0 to infinity. And so we've got what? -1 to the n. And now, of course, we just have 1 to the 2n plus 1. But we still have alternating. It's even easier. Now that's just a 1, so we still have a nice alternating series. So by the same argument, we get convergence. It just, the pluses and minuses are offset by 1. And just by the same argument, convergent alternating series. So we include 1. So now we can go back to our series and basically say that x can live between -1 and 1, including the endpoints. Remarkable result. So we're like, wow, there we go. Right there. So you're thinking, again, this would end up in a chart. These are nice Maclaurin series. And you're thinking, we extend the Taylor polynomial to infinite series, and then of course replace C with 0. This is what we would get. So what we're doing here is all legitimate. It's the same process because, like I said before, the convergent power series is its Taylor series. So we're doing a Taylor series, a Maclaurin series, without computing coefficients. This is so much easier. I mean, of course, there's a lot of work to do, but you know, let's face it. You know, you want to start taking derivatives of inverse tangent. Oh my goodness, that gets crazy really fast. We're thinking, wow, look how simple this is. At least these are techniques that are doable and based upon what we've already been doing. We love derivatives, but derivatives of certain functions get really messy really, really fast. Okay, so what I want to do is look at a couple of examples here. There are ways to approximate pi utilizing this series, making some adjustments with some trig identities. So often what will happen, ladies and gentlemen, is that you'll say, well, this series doesn't converge too quickly. So we might want to make an adjustment to it utilizing a trigonometric identity that will quicken the process. So many mathematicians that were instrumental in developing the idea of the calculus found these things out because, I mean, of course, everything was tabulated by hand. And so they would make adjustments in order to get a quicker convergence. You know, you don't want to have to add up 500 terms. You'd rather add maybe 6 or 7, you know, just enough. And then with the alternating series test, you're like, oh, that's not bad at all. Look what we can do. You know, it's the thing that makes this doable is that you have all kinds of refinements that you can do. And of course, all of the great mathematicians that preceded us work with these. And of course, they shared their genius with us. Now, let's look at an example. I thought there were some interesting problems here with the differentiation term by term, and there was a nice probability problem. And let me see if I can find it. It was really kind of nifty. Let's see, I'll do this one. Let me do this one first, and then we'll make a segue. Let's see, where was that example that I did with the probability? Yeah, we did x over 1 minus x quantity squared. And let's see where I do that. We'll just probably do that one. Let's see. And let me, because I want to break this up into 2 pieces. So let's see, yeah, let's look at this one. I want to do a differentiation example that we can segue into a probability problem. So here's an example. So let's see here. Yeah, determine a power series for 1 over 1 minus x to the power 2. And then we're going to rig this using cheap because we're lazy. And then use to write, I'm trying to put together two problems so we get more bang for the buck. Use to write a power series for x times that. So that's easy to do. If you get a power series for this, you can get this one just by multiplying by x using the properties, algebraic properties of the power series. So I want to kill two birds with one stone. So first we observe, let's just take some derivatives. The derivative of 1 divided by 1 minus x, obviously you see that that's what's going on here. This will be the derivative of 1 minus x to the negative 1. This is where the geometric series is very valuable. Okay, so when we differentiate this, of course, we'll get the minus 1. So we have the minus 1 minus x to the negative 2. And then, of course, the derivative of the inner function is just negative 1. So the negatives absorb. So we just get what? 1 over 1 minus x quantity squared. Now, of course, you can do several levels of derivatives, but this kind of gives you an idea, just like what we did with the integrals. We noticed a form that was interesting. That is, with the integral formulas, we saw, oh, this integral formula is the integral of something of a geometric sum. Rewrite the geometric sum as a power series and then integrate term by term. Well, see, what we want to do here is the same thing, the same process, but instead of integrating, we're going to differentiate. So what we see with this simple calculation here, well, it's simple because you've had calculus 1, is that the derivative of something geometric is equal to the function that we're interested in creating the power series. So now, again, we'll say this equals this, apply the differentiation term by term. So it's the same technique. So, but we don't have all this issue with the indefinite integration and the constants. Differentiation, at least in this case, is simple. So this implies that 1 divided by 1 minus x quantity squared, we just have d dx. Now, this is just our plain Jane geometric series. This is geometric. This is what we live for. No work involved, right? So we have the integral or the series n equals 0 to infinity of x to the n. Thinking, wow, can all problems be this easy, Professor Ron? And what's the answer? Obviously not. Okay, so now we can differentiate term by term. So let's flip it. N equals 0 to infinity. And now, again, when we differentiate, we bring the n down. This is so simple, we don't have to add the extra step, x n minus 1, right there. So when we differentiate term by term, we just apply the power rule to x to the n to give us n times x to the n minus 1. Now when we look at this, we're thinking, okay, well, no problem here. This, when n is equal to 0, we just get 0. You could leave it like this, but if you like, you can just go ahead and bump this up to n equals 1 because the n equals 0 term is 0. Your choice. So if you like, you can do this. So this doesn't take any time. This is like super simple. Now, what we can see in this particular case And notice here, if we do the replacement bit, if we let n equal or x equal 1 or -1, we just get divergent series. So not even close. So this will just be, in this case, x between what, -1 and 1. The endpoints diverge clearly. Endpoints diverge. So we don't get the luxury of at least even getting 1 in this case, like we did with the log and 2 that we got with the arctan. Just not going to happen. So now if we look at this, this implies that x over 1 minus x quantity squared will now be x times the series. Because again, 1 over 1 minus x quantity squared is this series. So this is x, n equals 1 to infinity, n times x to the n minus 1. And if you multiply through, you just add one more power of x. So that gives us x to the n. So I thought this would be an interesting way to develop a series that helps us with a probability problem. Okay, so there we go. So when you multiply a power series by a finite power series like x, it's like, well, how simple is that? This is a computation that we do all the time. It's just like multiplying polynomials. So this gives us plenty of power. Now, when you think about this example here, when you study probability at the university, probability is a beautiful, beautiful theory that uses real analysis. But there's a nice example here that I saw in your text that I thought, this would be a great way to show them about the term-by-term differentiation and then give them a probability problem. So here's the problem with probability. So it says example. Here's the experiment. Fair coin is tossed. Fair coin is tossed. This is called the geometric distribution. And then it says the probability. Again, you don't need to know probability. We're just going to use the calculus to solve the problem because I'm going to tell you what to do. The probability that a head occurs on the nth toss is, and this is written this way, that is, we have the probability of a head on the nth toss. It's like a random variable. The random variable is the toss. So it can take on values of 1, 2, 3, 4, 5, 6. And we might say that the probability that the random variable equals n will just be geometric. That is 1/2 to the n. Since we know if you've got a fair coin, the probability of a head on one toss is just 1 divided by 2. And so this just multiplies. Again, if you've had some probability, this may make sense, but don't worry about it because it's not gonna make any difference in the problem. Then the theory says, by definition, the expected value. I always like to throw in a probability problem. Back when I was doing face-to-face, I did a different problem because I could be more of an actor and get the class engaged, but this works better for online. So now the expected value of the number of tosses required. So you might say, well, how many tosses would we expect to have to do before we got ahead? And you're thinking in your mind, you know what it is, but let's see what the theory says. We say expected value that the random variable has the value n, and it looks like this, and you're going to say, oh, that looks familiar, Professor Ron. N equals 0 to infinity, n, p of n. So a lot of times when a problem will ask you to sum a series, they're asking you to do something like this, where you have used differentiation term by term. And that's where you can get a nice formula and you're like, man, we're cooking with gas now. So now you say, okay, well, P of n is just what? So this is n 1/2 to the n. Now when you look at this and you think about this particular example, you can see here that when n is equal to 0, we just get 0. So this is mimicking that, where x is 1/2. Okay, so you're thinking, when you look at this problem, you're like, oh, okay, so this problem that we just computed that Professor Ron asked us to do helps us solve this problem. You see? So this is why you really have to know a lot of calculus before you take real probability. And then, of course, if you're going to take the real probability, you need measure theory. You need a more advanced integration theory. It's like you can't do anything these days without calculus. I mean, if you want to be a financier, you have to know calculus. So it touches everything. So now we can say, all right, well, we can do it. So using this, so I'll just say by star, we have the sum n equals 0 to infinity, n 1/2 to the n. Of course, the n equal 0 is just 0, so you can just replace this with n equals 1 if you like. They're still equivalent, there's no difference. So now we've got this formula, and then we have the value of x. So this will equal 1/2. Again, here's our formula. Remember, this is the formula. So we have 1/2, 1 minus 1/2 squared. This is kind of like what I did at the beginning of class. Same thing, and this is exactly why I'm doing this now. There's a reason to my madness, ladies and gentlemen. And if you follow my lectures and you study my lectures, you won't have any issues on the test. But I don't think most of you believe that. It's just that I studied under some of the most brilliant minds in the world at Carolina and Texas A&M. And when I would go home, I would rewrite my notes at least 2 times. And then I would master them. Then I would go to the book. But again, that took forever. And my colleagues in grad school thought I was absolutely crazy. But if they ever needed notes for class, who did they come to? They came to me. And I said, I need to charge you for this. You need to take better notes. Okay. So when you look at this, you're thinking, well, we can do this. This will be 1/2. And now we have 1. So we have 1 minus 1/2. So we have 1/2 quantity squared. So we've got 1/2 times 1 over 1/4. So that'll be 1/2 reciprocate times 4, 4 over 2, which is 2, which is exactly what you expect. You've got a fair coin. So if you're tossing a fair coin, you're thinking you're going to need, on average, 2 tosses before you get ahead. Now, that's the expected value. You see the geometric probability here that you're tossing. You're basically saying the probability that you have success on the nth toss. Okay. So of course, for 1 toss, the probability of success is 1/2. You see? So the key is again, how do you phrase the probability in a mathematical way? And so you can see that, at least in probability, in discrete probability, that can even involve an infinite sum. And then when you have a continuous probability function, density function, that will merge from the infinite series to the, or finite series to the what? To the integral. Okay. So the thorough study of probability requires that you understand calculus. So again, as you work your problems, if a problem suggests that you actually do a sum, you can say, well, I need to figure out, using differentiation, a nice formula. And once I have the nice formula, I can sum things all day long, but it just requires you to come up with something that will suit the problem. Because if you look at this and say, well, I don't know how to do that, but when you think about the differentiation term by term, using the geometric series. And then of course, multiplying this by X, you get the exact series that you need. Okay, so none of this is set in stone, but you can see how the mathematics can be worked to solve the problem in probability. I think that's amazing. Now, one thing I want to share with you is an example with the arctan. And I'll just give you a nice identity here. This is something you sometimes do in pre-cal, but I think it gets left out due to level of difficulty. So what I wanted to do was the following. Remember, I mentioned the fact that sometimes if you have a convergent series, it might be kind of slow. So for instance, we will just note if we have inverse tangent of X equals n equals 0 to infinity, -1, X to the 2n plus 1, of course, that's alternating, 2n plus 1. So when we did this, remember, here was the series that we got right there that I just wrote. Right there. This one right there. And what we note is that the convergence is slow. Convergence is slow in the sense that you need lots of terms. Okay, so mathematicians notice this, and you can also try this and say, boy, this is kind of slow, because when you look at this series, again, when n is equal to 0, we get X, n is equal to 1, we'll get a negative, so we get a 3. Kind of looks like the logarithm. N equals to 2, of course, we'll get the positive, so we get a 5. I'll just write down one more term. So you see the pattern here. That's the pattern. And since the inverse tangent of 1 is pi over 4, for instance, the inverse tangent of 1 equals pi over 4. This series provides a method to approximate pi. So when you think about this, you're like, oh, okay, that's like doing the logarithms. If you want to try logarithm of 1.2, where, so of course the X would be in this case 1/5. Same deal. So in order to make this problem more manageable, you can use a really nice identity. The following identity, the following identity will improve the convergence, will improve the speed of convergence. And it looks like this. That is the inverse tangent of X plus this kind of look, it's almost like the cofunction identity, but then you're not putting inverse cotangent here, so not quite. So inverse tangent of X plus inverse tangent of Y is actually the inverse tangent of the quantity X plus Y divided by 1 minus XY. Of course, that's unambiguous, but you can throw in that if you like. Now, and of course, what's very important here is that the range of the inverse tangent is negative pi over 2 to pi over 2. So this sum here must lie there, otherwise this falls apart. So we need requirement. This is important, requirement. That is inverse tangent of X. Well, everything always has a hiccup, okay? We have to abide by the range and domain. This would mean that the sum here of these two inverse tangent functions must live between pi over 2, negative pi over 2 and pi over 2. because that's where this lives. Otherwise, this would be violated and wouldn't make any sense. It's hard to sometimes tell my pre-calculus students, if you don't respect the ranges and domains of the inverse trig functions, you're just writing down things that don't exist. So you all might wonder why I'm so particular about things. It's only because we want to make sure that what we're writing down actually does have some mathematical sense. So now what you can do here, this is a simple proof. I'll just kind of sketch it out. For instance, if you let alpha equal, I think this will work, the inverse tangent of x plus inverse tangent of y. You kind of look at it and say, well, that looks like the sum formula, addition formula for tangent. And that's what that is right there if you look at it. So this is maybe not so bad. So now you apply tangent. And that's going to give us what we need. So we can say that tangent of alpha, because if I take the inverse tangent of that, I get that. So I'm thinking that the tangent of this will give me that. So we're done once we reciprocate it or invert it. So this will be tangent of, let me write it out. Inverse tangent x plus, I won't skip this step. I don't, if I leave out a step, it's only because it's an obvious thing. Add 1 divided by the new power. But here I need to write this. So this is the A and this is the B. So this will be tan of inverse tangent of x plus, using the addition formula for tangent, tan inverse tangent of y. Remember, you get the tan A, tan B divided by 1 minus tan A times tan B from pre-calc. And then, of course, we get minus tan of inverse tangent of x times tan of inverse tangent of y. But of course, these all collapse by the inverse equations. So this is x plus y. I told you it was easy. Divided by 1, and then of course this is x and this is y by the inverse. So equivalently, if you apply the inverse tangent, alpha, which is this, inverse tangent of x plus inverse tangent of y equals inverse tangent of x plus y over 1 minus xy. So you're thinking, well, what does this have to do with anything? Well, it does improve the convergence. So what I did, I was looking through the ebook and I saw an example. It says, we'll use this identity, and then it talks about this discussion and all. And I thought, okay, well, here's a nice example. So with this, we have the following. That is inverse tangent of 1/2 plus inverse tangent of 1/3 equals pi over 4. Basically, when you do 1/2 plus 1/3 divided by 1 minus the product, which is 1/6, you get 1, and inverse tangent of 1 is pi over 4. So this gives you this specific example. So now what we can do is multiply this by 4 and use this series with these to get quicker convergence. So let me show you. So now, so equivalently, if we multiply through by 4, we have 4 times inverse tangent of 1/2 plus inverse tangent of 1/3 using our nice identity. This should be exactly pi. So we can use this, to approximate pi with infinite series for arctan. So that's the key here. And this actually improves the process. So let's just see what we get. So in this particular case, ladies and gentlemen, I use 9 terms. So I wrote out all the terms. So notice here, this one here, I wrote out a bunch of the terms. So I'm going to fill in this series with 1/2, and I'm going to fill in this series with 1/3 and multiply by 4. Okay. And I did these up for 9 terms. So here's what we get. So we get the following: 4. So I'll get 1/2, and I'll go ahead and do the actual powers. So I'll write them out. So we cube, we get 1/8 over 3 plus 1 over 32. This made it easier to put it into Google, minus 1 over 128 divided by 7. I just went up to 9 because I got a little bit lazy. 512 over 9. Okay. So approximately, and then plus. So again, remember this is x cubed over 3, x to the 5th over 3 over 5, x to the 7th over 7, etc., with the plus minus. So this was the 1/2, as you can easily see here. And then I'm going to have powers of 1/3. And I actually multiplied these out: 1/3 in my, well, not it, well, some in my head, but just on paper. 1 over 27. And then of course, 27 times, so when we get to the 5th, we're going to do 9 times 27. That's going to be 243. Yeah, that's right. Over 5. And then multiply again by 9. 9 times 243 will be 2,187. And then 9 times 2,187 will give you 19,683. How funny. We're 9. Okay. Now at this point, I use Google. And I wrote these this way because I remember for one of your classmates, I did the alternating series with Google, alternating with, 1 minus 1/2 plus 1/3, whatever. But Google's really nice because it's so big and you can check your work and you can scroll back if you make a mistake. But the thing is, when I did this and added with Google, I got two decimal places. So I got 3.141, actually 3 decimals, 74119743. So you can use Google. And then of course, I compared this to the actual pi approximation. So from the Google with pi, you have 3.14159265359. So we can see with just these few terms, look how much accuracy we get right there. So the idea here is that if you just use the series as it is, you may need to develop up to 100, 200 terms just to get maybe 1 decimal place, which is crazy. That's insane. So here what we're seeing is that we're securing 3 decimals with just these few terms using this remarkable identity. So when I say that the pre-calculus is tantamount to doing calculus, I mean it. I know a lot of times when students take pre-cal, they don't see the reason in doing any of it. But see, that's when you have to think outside the box. Remember the movie Hidden Figures, the African-American women at NASA who just blew the roof off with their brilliance? I remember the lady said, you have to look beyond. She said, they said, how did you do this? She said, I look beyond. And so in class, I would do this and they'd say, what does that mean, kids? I said, oh, Professor Ron, we need to look beyond. Well, that's what you have to do here. You have to think about what's going on and look outside the box. When you're taking a class and your professor says, you need this for calculus, but you don't take it in. You just kind of get through it. You do mediocre work. And then when you get to calculus, you don't know what you're doing because you've got to look beyond. I keep telling you how you're going to use this in Calculus 3, differential equations, linear algebra, partial differential equations, engineering mathematics, all of this stuff you will continue to use. So you have to look at this work as looking beyond. You are now mature enough, you're in a calculus 2 class, that you should understand that. So when you talk to your friends and your colleagues who are just belly aching about math, tell them, okay, you've got to look beyond. You've got to think, what am I going to work with? What am I going to do with this later? And here's another thing too, ladies and gentlemen. You see, with combining the infinite series with the pre-calculus identity, we get a beautiful approximation method for pi. And so when you think about what we're doing, you see that all we're doing is building more scaffolding. We're talking about the same things and we're just adding more stuff, and we just keep adding, just like this. And so those of you that eventually go on to maybe graduate school beyond the bachelor's degree, say if you get a Bachelor of Science in mathematics or physics or mechanical engineering or computer science, you're going to see when you get to grad school, you're going to be doing the same kind of problems, but you're going to stepping them up. You're going to add more scaffolding in more detail, because the problems that we solve are the ones that we work on now. We just put more detail in to figure out how to do more refined problems. So what's interesting now that we see this, we want to take our thinking to the next level. For instance, we use this procedure with the geometric series to get a power series. How can we use this? How can we add to this? Okay, if we can't do this, what else do we have? We've got the Taylor series. And so now we can develop new series using Taylor's theorem, add to it the series we've developed with geometric series, and then add the binomial theorem. We'll be like, we'll be cooking with gas. And then, of course, in the next section, there'll be a nice list of famous power series. It'll be like an integral table, which will be a list of power series that you can use. That is, you can combine power series to produce new series in algebraic ways. So we're going to find that we don't always have to start at square one. We don't like to do that. We don't like to have to start over every time. So we're going to use some of the concepts that we've set up here and add the algebra of the power series to create new series. So I hope that you have enjoyed the lecture today. It's certainly a joy to teach this material. This is some of the most interesting material you will learn. And then, of course, when you get to power series solutions in differential equations, you will be manipulating series, and that'll be a blast. I'm sure when you get to it, you'll like it. I've taught a course in that many years at San Jac. Right now, with the online, my colleague, Dr. Wiggins, is now mainly teaching the DE course because he set up a nice homework system for that. So some of you may be eventually taking his course. So I wish you well today. I hope that things are going well. I'll have my one office hour today. And of course, I've got the 3 on Thursday, which again, I think I must have been insane when I set that up. But that's probably one of the most popular days for Professor Ron. So good luck with your studies. If I see you at office hours, fine. If not, send me some WebAssign messages. And I look forward to continuing the saga to complete the infinite series. And then, of course, after that, we'll move on to the parametric equations, and you'll get a little rest from all of this arithmetic, but of course not much. So everybody have a great day. Thanks again for your attendance.